I think so. I need
Okay,
to.
okay.
Yeah. Okay. So once we see ourselves here, I think we are good to go.
Okay.
Okay. So we just see in one screen, but I think that's fine, right?
Yes.
Okay. So hello everybody. Welcome to the next talk in the CERIAS seminar series for 2017 spring semester. So today we have a very distinguished speaker. Her name is Limin Jia. So she's an assistant research professor in Carnegie Mellon University, CMU in Pittsburgh. And she has done lots of work and works on very different aspects regarding formal methods and security. Today she is going to talk about some of her work on mending the gap between the theoretical and system security research. It will be a generic talk, but I think she'll go into the detail for some of those topics. So, please.
All right. Oh, sorry, I have my mic on. All right. All right. Nice. Thanks for coming. Nice to be here giving the talk. So I'll start by saying, quoting Yogi Berra, which is an MLB player. So he says, in theory, there's no difference between theory and practice. In practice, there is, right? So I want to map this onto software security. So I have this x and y axis. In the axis is about the formal guarantees. The more to the left, the weaker the guarantee. The more to the right, the stronger the guarantee. And then on y-axis, we have features, right? The closer to 0, you have fewer features. Up on top, you have more features. Interesting. All right. So for the working systems actually live up here. You have a lot of features, but you tend to have fairly weak guarantees, right? You want to build a system that actually works. And then in terms of models, abstract models, you tend to have a lot of formal properties because you can actually analyze them a lot, but they tend to have fewer features because it's easy for you to analyze them. So of course, ideally, what we want to be is up here in this small bubble where we want to have fully verified system, right? We want to have a system that actually works, have all the functionality you want, have all the features you want, but also have really strong guarantees that you care about. So in terms of research, a lot of the systems research tend to be in this bubble, right? If they build real working systems, have lots of features, but maybe in terms of the security guarantee or any of the formal properties, maybe people care slightly less about. So in terms of theory research, we tend to stay closer to this bubble. We tend to build models, abstractions, prove properties about it, but because the difficulty of doing proofs and building models, we tend to throw away lots of features. We claim they're non-essential, therefore we're going to abstract them away, right? So that's where we are. So we do have a very selected group of researchers actually are doing research over here, especially recently NSF find a big project called Deep Spec. So we have Princeton, Yale, UPenn, maybe some other university here, where what they really want to do is they want to produce a tool chain where you can write program in C, but at the end of the day, I can show you that the machine code generated through a verified compiler that the property you have actually apply on the machine code, right? You can imagine here, only selected systems can be done this way. If I'm talking about a hypervisor or a kernel, that can be done because they require a couple thousand lines of code to actually go through. However, if I'm talking about browsers, this is going to be really difficult, right? The browser have a lot of really complex functionality. It's going to be extremely hard for me to say I can generate a fully verified browser, right? So we do have projects here, but it's very selected project that tend to cover important but small software. Sadly, this is where the real software companies are going. They're adding more and more features, but they're actually introducing more and more bugs, right? So sadly, the most common bug we see these days are still buffer overrun, all the really simple bugs, but they're not disappearing. They're actually appearing more and more often. So in this landscape, for my research, I'm somewhere in this blue dot. What I want to do is I actually want to analyze the property of systems. I want to be able to construct provably secure systems. So what I'm doing, or the theme of my research tend to be, I actually want to start from a real system, a real browser, a real Android operating system, or I'll talk a little bit about this if this and that framework. We look at the real system, then we want to figure out what are the nice properties we want to have about this system. To use formal modeling and formal techniques to actually, at the end of the day, show that these are the property we want and show that the design, at least design level, we have these properties. The problem with doing this kind of research, or the challenges are that often it's really hard to balance the trade-off between having functionality versus having stronger security guarantees, right? If I just throw all the features, then I can build a system that's not very useful, but I can show it's fairly secure. But if I want to have all the interesting features, that often increased my difficulty of constructing a security proof about that system. All right, so in terms of the projects I'm working on, so I can sort of draw an axis of theory and practice. So roughly, I have a few blocks of work. So one main block of work is about information flow security. So in this talk, I'm just going to talk about information flow on Chromium. If I have time, I'll talk about using information flow to actually analyze the security and privacy of if this and that framework. In this space, a more theoretical topic is something about compositional information flow security, where we have upcoming paper about compositional timing-sensitive non-interference. So there's lots of work in this space. And then the more practical ones is we actually have infrastructure that we actually taint pages. Then using that taint, we're actually thinking about how do I use it in infrastructure to profile web pages, to figure out what the web page is trying to do. So another block of work is program analysis and verification. So this is a fairly new field for me. So in the past, I've been mostly doing model building and doing proofs. So using tool to analyze things is new to me. So I have my collaborators who are experts in program analysis to help me out. So here, there are actually lots of interesting problems that we can solve. So for example, now Node.js is becoming really popular. A lot of big companies are trying to move toward Node.js, saying that we don't want to program in Java anymore. Instead, I want to program in JavaScript. That's a really easy language for the programmer to use. But the problem here is that in Node.js community, you use a npm package manager to essentially import a bunch of packets from other people, and then you can write your program by importing other people's package. So there could be a huge dependency tree depending on which package which packages you depend on, and all these packages that you depend on are contributed by other people that you don't even know. Right, so here, there's a huge security problem in this paradigm. So we're trying to figure out what's the best way for us to design some sort of analysis tool to help programmer understanding what's the problem there, warn them that there could be risk if you import these type of packages and so on. So yeah, I'm working on program verification with Professor V.S. Sakar, CMU. So here, what's interesting is that often you can model network as a distributed program, but network has its own patterns and idioms. It could be that by leveraging this, we can make verification more efficient. I also collaborate with people on the CI side, where we actually look at accountability and blame. So if something goes wrong, how can I figure out who the right person to actually assign blame on? So this is essentially the space, but in this talk, I'm just going to talk about two topics in the information flow space. All right, so in terms of information flow, what's interesting is that when I go back to this particular diagram, on the theory side, actually every year if you go to any of the somewhat theoretical security paper, you will see a lot of paper being published about new models and definitions about non-interference, which is a key security property about information flow control systems. Numerous papers appear every year. But in reality, the information flow has not been used as a real or practical security mechanism in any real systems. Right? So when Android and Chrome got pushed out, that was actually fairly recent. The only thing they can think of is still using permission system, using access control system. They really didn't think about having information flow as part of their security enforcement system. What I'm interested in is really somewhere towards here, where I can use these strong enforcement mechanism information flow to actually eventually put it onto real system to actually help the user to protect their private data. But first I want to actually motivate information flow. So here I have a few images on the left. It's on the left, right? So on the left, they're mostly older systems where you have the server client paradigm, you have your own PC. In those days, the security goal are in general you want to, for example, guard your file system against unauthorized users. You want to protect kernels from application process and so on. And the standard mechanism we develop is separation access control, right? So these mechanisms are still relevant today, very much relevant today. We still use separation and access control to protect our resource and our systems. However, on the right-hand side, these are newer platforms, right? So nowadays we actually use browsers and use phones to access a lot of services. Right? I do my banking mostly through my app. When I make an appointment with my doctor, I actually go to the web to actually make my appointment. So that means that in this system, now there are new goals. There are actually lots of users' private information flowing through this platform, right? As I'm typing my credit card into the browser, actually browser would hold this credit card number in the system. This number is flowing around in this system, and then eventually it goes out, right? So here we have additional goal to actually protect these kind of user-sensitive data that's been put into the system, right? So here we also in a time where it's very easy to install third-party applications onto your computer, right? You just go to the App Store, you say I want to install this, want to install that. It's really easy to install potentially malicious applications. So here, in addition, we also want to protect applications from each other. Right? So it's very easy to have mutually distrusted applications installed on the same platform. So now, in these systems, for example, in Android, they're still using permission-based systems. However, I want to argue that the permission-based system is not enough to prevent the information leakage or privilege escalation. So here's a standard example that you will get when people ask you why permissions are not good enough. So in this example, I have a shopping cart, a shopping application, and then I have a camera API. So in Android, if I don't want shopping application to use the camera, I will not give shopping app the permission to access camera. So if the shopping cart tries to directly call the camera API, this will be stopped by Android runtime because the permission check failed. However, I could also install another application which might be a barcode scanner. Now, because this barcode scanner needs to use the camera to scan barcode, so the barcode scanner is allowed to or given permission to access the camera API. Now, in addition, this barcode scanner export a public API that essentially can be operated by anybody to eventually use the camera going through the public API. So what happens here is that your shopping app, when trying to directly access camera API, will be denied. But when they try to call the public API exposed by barcode scanner, then access camera this way, this will actually be allowed by the access control, right? So the access control is a very immediate check between the caller and the callee. But here the property we're looking at is actually a more transitive property. We're looking at the entire trace of the execution, right? If I have information flow control, I will be able to stop this. But just using the permissions that's on the phones, I actually can't do this. This is one example here. So the browser has similar problem. So in browser do have SOP, system margin policy, do have CSP, content security policy, and for browser extensions, Chrome, I think Firefox also, they have this permission system where the extension would ask for permission from the user. Based on what permissions granted, the extension can do certain things and barred from doing other things. The problem there is that even given all these mechanisms, we still don't have fine-grained control over data sharing within the same page. So for example, here there are some actually real-world malicious Chrome extensions that are trying to steal or hijack users' Facebook account. We also have news about malicious extension trying to hijack the cryptocurrency wallet. So these are not hard to do because the moment you allow the extension to inject script into the page, the script essentially have all the access to whatever this the URL of the top page. That whatever resource the URL of the top page has, now the injected script can access the same data. All right, so here is a so that's what happened in the news. So here is a simple example, essentially model what's happening in those scenarios. So I'm going to use the password manager as an example. This is just example, but it's similar to the scenario I showed you in the newspaper clip. So what's going on here is that I have a simple page. Let's say it's a CM page. On the CM page, there's a form where there's a user and password field, and the user can put in the username, password, and log in. Now, the user does is the user actually installs a password manager. The password manager essentially, the first time sees the password, to store the username password in local storage, and the next time when the user goes to the same page, the password manager would load the password and fill it for the user. So at the same time, the user install another extension that's actually malicious, or it's called the evil. So it's actually a translation extension that happen to be doing extra stuff on the side. So what could happen is that when the user goes to cn.com, the password extension will read the password from local storage, send it over to the content script, then the content script would actually fill the password on user's behalf. At this time, the evil extension can also inject script into the page, and this evil script, this yellow color CS, would actually be able to read the ID and the password from the DOM and then send it over to the evil extension. So that's how user-sensitive password gets leaked to the evil extension. So this scenario is exactly how the evil extension can hijack Facebook account, and also how evil extension can steal the cryptocurrency wallet, right? So once the content script on the same page, this content script actually has full access over whatever is on this page, right? So this is allowed in the browser, right? Right now, nothing prevents this from happening. So what I'm arguing is that given these scenarios, given the additional goals of protecting user private data, we actually need new mechanisms. In addition to separation and access control, we also want information flow control, right? All these examples actually involve more than one step of information being passed around, and we want to follow this trace of information and eventually stop the bad flow from harming the user, right? So that's the motivation part. So I'm going to talk about one specific work that we did on Chromium, which is the open source version of Chrome. So here, what we want to do is we want to prevent information leakage in the browser, like the one I showed you in the example. But at the same time, I also want to also allow desired information sharing, right? So right now, if I embed a script from ad.com, now this script would actually have full access, or would be running considering from the same origin as the main page, right? So here my main page is CNN. Even if I load the script from ad, that script would be considered as if it's from CNN as well. So in addition, I also want to be able to construct a reasonable model, and I want to prove security properties about the enforcement mechanism that we're going to develop on this browser. So here our contribution is that the first one is a practical contribution. We actually designed and implemented a coarse-grained dynamic taint tracking on Chromium. I'll show you how this works in a sec. So essentially, in our infrastructure, we actually cover almost all the parts of the browser entity, and being able to allow existing behaviors of this browser. So the second part is that we actually allow a rich policy specification to allow the web developer to say how the information should be shared, and so on. So then the second part is a formal contribution where we say, okay, tainting tend to be an easy way to implement information flow control. Tainting tend to be easily retrofitted into an existing system. Now the question is, what kind of security property can I get by using tainting, right? Do I actually get really secure system, or the system is not as secure as I expected? So what we did is to formalize the formal properties of tainting, and then prove that our design has this property. This property, for all the information flow property, is always called some sort of non-interference property. All right, so we're not the first one to do this. There actually quite a bit of related work. People have tried to enforce information flow security using static approaches for a while. So there are information flow type systems. So essentially, instead of just having int and bool, I have int secret, a secret int, or a public int. By labeling variables and expressions using these kind of types, a type system, meaning the compiler can actually check whether your program can protect the secret int or not. Right? These are all static approaches. There are also static analysis approach using self-composition to actually do this. Now, in our setting, this is going to be extremely hard, because on the web page, I actually don't have all the JavaScript ready to be analyzed, because I'm going to embed some script from the ad, and at runtime, the ad.com will ship me some script to run in my context. Right? So for me to do static analysis is going to be extremely hard. Now there are also other taint tracking, mostly on JavaScript. So there's JSFlow, there's work on implementing a WebKit through the DOM, and so on. So here they're actually tainting at the variable level. They say, oh, this variable URL is a secret, or this password field is a secret, and they follow the variable through the JavaScript engine and try to figure out whether at the end of the day there's a secret being leaked or not. So here they are much fine-grained and normally only cover the JavaScript engine part of the browser. So it doesn't go beyond, say, cookies or history or other parts of the browser. So in terms of browser itself, FlowFox is a pretty well-known work. So they're not using tainting. So instead, they essentially have a new JavaScript engine, use something called secure multi-execution. The idea is that if I know there's some secret input to my system, I know there's some public observer output out of my system. What I'll do is I'll run 2 copies of the program, and in the first copy, I would allow the first copy to receive secret, but not allow them to output to public channel. And then in the second copy, I will run as if it's the attacker. I will not give it any real secret input. I will give it default value, and I do allow it to output to the public channel. And at the end of the day, I'm going to splice the input and output together across these 2 executions. So this is an approach that is going to get 9 difference for free because the mechanism itself manually separate the secret input from the public output. However, because it's secure multi-execution, that meant that for each script you have to execute multiple times. Or it's not a super efficient way of doing this. Again, this is just focused on the JavaScript part of the browser. So the concurrent work with us is this system called COW. It's a confinement system. So it's actually, the idea is fairly similar to ours. They're going to look at each entity in the browser, and then they assign a information flow policy associated with each entity, and then the runtime will try to enforce some sort of information flow property based on the policies. So here it's more of a systems work. They just demonstrate that this works, but there are no modeling or proof that the system give you some sort of 9 difference here or not. All right, that's related to work. So now I can actually talk about what we're doing. So here essentially an approximation of what's in the browser. So on the left, I have something we call dynamic entities, meaning the things exist when you are browsing. Once you close the browser, it will go away. So for example, you have a lot of tabs, and in each tab you have your DOM tree. You might in addition to your main DOM, you actually might have a DOM for iframe pages. You might have page events, for example, things like on click or on focus and so on. And then you have a bunch of scripts, right? These scripts could be coming from the same origin, could be third-party script, could be content script injected by the extension. For extension, you actually have each extension have one single core that will be running when you start the extension. So on the right-hand side, we can have something called static entities. So these are things that would stay when you close the browser. So for example, cookies, history, bookmark. We also list browser API here. So essentially, it's something that the user, it's a state that will be kept by the browser. When you close the browser, it will stay. When you open up browser again, you will see the previous saved state from the browser. So what we do is that instead of at the variable level, we're going to take each entity and assign it a information flow label. I'll show you what label, the concrete label, in a bit. So this label essentially represents policy talking about what type of secret this entity is allowed to learn, what type of API this entity is allowed to access. And each of the communication between entities are monitored, are mediated. So the reference monitor essentially would check when 2 entities are trying to communicate with each other. So for example here, so when, say, the extension core try to inject or try to send some data to the content script on the page, so when this send happens, there would actually be a reference monitor check that the sender's label is compatible with the receiver's label. So similarly, when the script tries to access the DOM, the reference monitor will check that this access is allowed, right? And of course, when the extension core trying to access browser API, such as clear all the cookies or change all the cookies, this will actually also be checked by a reference monitor. Right, so that's roughly how this works. And here, for us, we actually allow labels to change at runtime with tainting. So we could have an entity initially doesn't contain any secret. Upon receiving secret, we will change the label to mark that now this entity actually contains secret. Right. All right, so now what I'll do is I would actually go through an example step by step. I'm just going to use the password extension example to show you how do we do labeling and how the check is going to happen. So here, the first thing I'll do is I will have to, because I'm going to assign label to each entity. So here I have a CNN small cap page, and I have a little form with ID and password and login button here. The first thing I'll do is I would actually have to assign a label to this entity. So our label is composed of 3 parts. So the first part is what we call secrecy label. So essentially, it's saying what type of secret this piece of code has already received, and what type of secret this component is allowed to additionally receive. So I have two parts in the secrecy label. So on the left, we call it the current secrecy level. So here CNN, so we're essentially using the domain as the tags for secrecy. We're going to say that here is secret from this domain, from that domain, so on. So here, the left part is essentially saying that currently, because this page is loaded from CNN, so it's already containing secret from CNN. That's the left part. The right part is what we call ceiling, meaning that because we allow label to change when more secret arrive, so I want to put a cap on the maximum amount of secret a entity is allowed to receive. So in the ceiling, so we have some label called compound label. We use a dot notation. This is saying this secret belongs to CNN, but in addition, a different entity actually might modify the secret. So here, this is saying that the ceiling tells me that in addition to secret from CNN, I can also receive any secret that CNN dot anything. So essentially, any secret that belongs to CNN, but some other extension might modify the secret. So that's secrecy label. We have the current level, and we have the max level. If in future times, when this entity receives more secret, it cannot shoot over the ceiling. It has to be capped by the ceiling. All right. So we also have the second component is the integrity label. So in this example, I'm not going to use the integrity label at all. You can think of them as a glorified API permission. So if this actually it doesn't quite apply on the page for now, but if I'm talking about extension, you can imagine here I'm talking about what type of browser APIs that the extension is allowed to access. So the last one is what we call endorsement or declassification label. So essentially this is saying that, well, currently I know CNN, but I can actually turn around and declare that I actually don't have any secret at all. So that's that's action of declassification. And I'll show you how this works just in a little bit. So that's the label for the DOM. So essentially, when the page gets loaded, based on CSP, based on where this DOM is loaded, this policy is semi-automatically generated. So in terms of password extension, we're going to have policy for the core and also policy for the content script. These are two different components. So for the core policy, again, for the secrecy, we have the current level. So we have two labels. We have two tags in this label. So this is saying that this password extension have already seen the password from CNN and also have seen the password from eBay, right? So if you had gone to CNN, put in the password, the extension stored it, and then you have gone to eBay, the password extension have stored that password. So the current label is saying that the password manager has seen these two passwords. Therefore, the password manager know secret about these two different domains. Now the ceiling is saying that because this is password manager, so it's allowed to learn secret from any domain. So I'm going to have star dot password to signify that the ceiling would allow this to happen. Right. So for integrity label, I keep it empty. Now I have a meaningful declassification label. This is saying that I can remove my label. I can remove anything dot password. This means that if currently I know CN's password, eBay's password, I can change my label to show that the secret I'm generating is just eBay's password. So I'll show you where we use this just in a little bit. So now for the content script, it has a different label. So for secrecy, what's interesting is the ceiling. We have a dagger. So what's happening is that when I have a browser extension, there will be only one core running, but each time you open a new tab, the content script will be injected into that tab to run in the context of that particular page. So this dagger is saying I can receive secret, but I'll be instantiated once when I inject into the page, right? So right now it's dagger, but the moment I inject the content script into CNN, this dagger will turn into CNN, because on that page, this particular script can at most learn CN's password secret. Right, so that's the interesting part. So for evil extension, we have very similar label. So here the evil extension the core come with no secret, but it's allowed to learn anything that the evil extension have touched. For content script, we have very similar. This evil should be actually evil. The ceiling of the secrecy is very similar to the password's content script. All right, so now we can actually run this example to see. Yeah.
Hold on.
Yeah, that's fine.
Yes. have a question about the settings on the evil extension. So is that possible that the evil extension tries to claim that the it also holds that CNet, the password, the label? Is that possible?
It's possible, yeah.
Then, so it seems like there should be some sort of the what is that? Sort of the check phrase that the evil extension shouldn't claim such the policy.
So what would be dangerous, it would be evil extension have it in the ceiling. That means the evil extension allowed to learn this. So yes, so this is similar to when you install browser extension. The browser extension will say, this extension asks for all these permissions, do you allow or not? So that's a check would happen. We don't have automatic check right now.
Yeah, so it seems like in the current setting in the Chromium browsers, when we are actually installing the browser, installing the extension, and users sort of we are sort of pushing the responsibility to check the policy by the users.
Yeah.
And I think it seems like your system also has the same issues.
Yes, yes. So anything that have a policy, the question is always where the policy come from, who is checking the policy is reasonable or not, right? So and also there's studies showing that the user never care about when they're being asked, right? So now the question, I think there is some work, I would say related work, where they try to check whether extensions or Android apps are over permissioned. I felt like that's a more promising way to go. So when the extension asks for a certain label, I guess we have to check whether they need it or not. That requires a programmatic static check of the code itself, right? So if you don't want to rely on the user, then we have to be able to automatically check some things. Yeah. So so I think in terms of information flow, usability is actually a fairly important issue, right? So here I write my policy this way. It may not be the best way to actually write the policy, right? People actually would have confusion about what the policy is about. Yeah. Other questions? All right, so we're doing the injection. So here, what I will do is I will try to inject the content script into the page. So there are a few checks needs to happen. So when I inject the content script here, because the content script itself doesn't contain any secret, so that injection will succeed. What's happening is I just need to instantiate the dagger with the parent page domain or the origin. So here instead of dagger, now it becomes cn.password, because now this content script is running in the context of the CN's page. So now what I want to do is want to show you the step where the core of the the password manager would read the password from local storage and try to send the password to the content script to be injected. So here actually we need to do a label check. Well, because what's happening is information is being sent from the core to the content script, right? So what they're checking is to see whether the secret that the password manager knows is a subset of the ceiling of the content script, right? So this is saying that the secret that the sender knows, is it a subset of what the receiver is allowed to receive, right? So unfortunately, this check will not succeed. The reason is that the password manager has already seen two sites password, so I have no way of knowing whether the password manager is sending me the right CN password or not, right? It could be that the password manager actually read eBay's password and try to put it into CN's page, right? In that case, it's actually insecure. However, here, because we trust the password manager, so we actually gave the password manager a declassification token here, right? We're saying we trust the password manager to actually remove any secrecy label that's in the form of something.password. So here, the password manager could actually declassify and remove eBay password, essentially change the label from cn.password, eBay.password to just cn.password. This is a very dangerous operation because by using the same operation, this password manager can erase all secret and start sending this to the public channel, right? But this is considered a trust operation. So after this declassification, the label of the core of the password manager turn into cn.password. Now this actually match the ceiling of the content script. So at this point, this sending is allowed, right? Now this password can be filled into can be received by the content script, right? So in addition, when we send the data over, initially the content script contains no secret. Once this password being sent to the content script, we actually have to taint the label of the content script to remember that now the content script actually contains send.password secret, right? So this is a way of doing the tainting step when the data is received by the content script, right? So the next step would be the content script would try to inject the password into the page. So what we need to do, this is again another information flow here. We need to check that the information being sent to the form is allowed to receive this password, right? So now what we're checking again is checking the current secret label, the relation between the current secret label and the ceiling of the recipient label, right? Here, because it's a wildcard, so this check would actually succeed. Now this password can actually be filled into this page, and then again we're going to do the tainting because initially this page is loaded from CNN, only have CNN password, only have CNN secret. Now I'm actually putting user's password in here, so now I'm going to change the label to be CNN.password to essentially taint this label to represent additional secret, right? All right, so that's essentially the step of putting the password in. How do we do declassification? How do we do tainting? All right. So now I'll show you if we have the right policy, how do we actually stop the attack? Right. The attack is the content script is on the page and trying to read this password. All right. So now the information goes from the ID and password to the content script of the evil extension. So we're going to do the same check. We're trying to see whether the current level of this ID password field, which is send.password, is a subset of the ceiling of the content script, right? Now here, this check would actually fail because the extension is not allowed to learn cn.password. Therefore, the reference monitor will actually stop this send from happening, right? So that's how we allow the content script of this evil extension to operate on other parts of the DOM, but not allowed to operate on the password part of the DOM, right? This is a fine-grained sharing and information flow control in the context of the web page. All right, any question here? Yeah, so here for all the information flow stuff, the big thing is you have to be super careful with the policy and also with declassification. The moment you have declassification token, it's going to be dangerous. Yeah.
I have a question about how do you update the label? So for example, let's say you have two extensions, and let's say one guy delete the field, and then the other guy updated the field again, and then how you actually come up with the new label which accommodating those two extensions.
So if I allow to do that, I just do a union. So tainting.
Just put that every information.
Yeah. So I check the ceiling. Have I hit the ceiling yet? If I haven't exceeded the ceiling, then I take the union of the label. That will be the tainting operation. Yeah.
But from the system's perspective, I mean, if you have too many labels, then that's going to be pretty hard to propagate, right? And
yes. So in terms of usability, yes. So depending on how much communication there is, you might be accumulating a lot of labels. But from what we are looking at I guess we didn't really interact with the page, but we crawled over a bunch of pages. So for the regular pages, we rarely see the communication depths more than 4. So the page loads itself, maybe load some CDN, when to add. If you're going to Google Analytics or double click, they will additionally load a few other ads, and then maybe one more. That's a complexity we see in ordinary pages. If you go through this path and you don't have really crazy read and write into the DOM, you tend to stay at a smaller label. But another thing we were thinking about is to cluster labels. So say that your main domain, CDN, trackers, advertisers, and then maybe if the user declare I trust Google, Amazon ad system, they would be bucketed into one, versus the untrusted ads and trackers, they'll be bucketed into another one. Instead of tracking all the domains, I'm going to track the bucket, which bucket are you in, then we'll be reduced to 3 or 4 labels max. That's one way we're exploring right now. But it's unclear in reality work or not. Unless we look at the real pages, we don't have the data right now. But it seems like for all the data, for all the OK web page we look at, they rarely go down to more than four different levels when they go down, try and talk to each other. Yeah. All right, so where am I? So in terms of implementation, we have to go into Chromium to actually modify things. We didn't touch the JavaScript engine because our entity is not a variable level. Instead, our entity is the entire script level. So the main thing we modify is actually the IPC call. So it's essentially inside the browser. Roughly, you have a browser process which is the glue of all your tabs. So in this browser process, this process is going to handle all the storages, handle the user, the UI, the user's input, and also handle the network request. And then for each of the tabs, for each of the tab of the scripts and the rendering engine you run, each one of them actually have a separate process. And when the user is typing stuff, this glue code would be in charge of sending IPC to the rendering engine to say, oh, hey, there's some change to input to the DOM. When something happens here, the user needs to know the IPC call will come back to actually essentially go into the network to grab more resources or go into the storage to store or read and write stuff. So these IPC calls essentially are the key parts we actually have to instrument our code. Here we have to actually, for each entity, when data are being sent back and forth between them, the IPC have to ferry the label across them and do label check. Right? So that's roughly where the modification happens. But in terms of modifying Chromium, it's actually fairly complex. We have to have a professional programmer to actually go and do it. None of our PhD students can handle the complexity of the stack trace. But now we actually have an infrastructure can actually do proper tainting using the Chromium. All right, so in terms of formal proof of security, what we need to do is there's no hope to prove anything on implementation because it's so messy. So instead, we want to say, categorically speaking, the kind of model, the kind of design we're working on is this sound, right? So what we do is we actually model the main parts of the browser functionality and then model the taint tracking part. And then we have to define the property that we think we can prove, because when you say non-interference, there are actually a lot of different definitions of non-interference based on your system. So here we define our version of non-interference. So essentially, all non-interference trying to say the attacker cannot learn in secret by observing public output or by altering the public input. Something like this. I think I have a more detailed slides after this. And then when you do the modeling, when you define the property, then you have to prove that the model actually have this property, right? So it's a little bit detailed about the non-interference. So often what you need to do is you need to define what's the secret in your system, what's the attacker's observation, right? So here we have the standard web attacker scenario where the attacker can own a web server, can inject script into the page. They might actually control some of the extensions and so on. So what they can observe is the execution trace, right? That include all. So if the malicious attacker have an event handler, then the attacker will be able to observe all the events sent to the event handler. If the attacker is making a call to the network and having requests coming back, then that will be the observation, part of the observation of the attacker also. So in terms of non-interference, we actually define something called trace equivalence-based non-interference. So what we want to say in terms of non-interference is saying that if I run the system, if I start with two configurations that they are the same in terms of the attacker components, but they might be different in the secret or sometimes we call it high component. If I start my execution in these two configurations, for any trace that is observable by the attacker starting from the first configuration, I should be able to find the equivalent trace starting from second configuration where the attacker can actually observe the exact same behavior, and vice versa. So what this is saying is that when the attacker sees a trace, it cannot deduce which configuration it's in. Therefore, it cannot know too much about the secret. Right? So that's roughly what we prove. However, the problem here is that we're not considering declassification. In this packet definition, we're now saying with declassification, what can we say? We're actually saying without declassification, here is what you get. Right? When we have declassification, we actually don't have a good theorem talking about declassification right now. So that's why in the future work, we're actually thinking about using knowledge-based non-interference to actually talk about in declassification what kind of knowledge the attacker would be able to infer based on the declassification. Right? So to summarize, so what's going on here? I said that I want to be somewhere here. So Chromium is obviously a working system, have lots of features. So I'm up here. So what we're doing is we actually instrument a real browser where we can actually do coarse-grained taint tracking. And at the end of the day, what we prove is that on the model level, we're proving the enforcement have trace-based non-interference, right? So there are gaps between a fully verified system and what we have. I mean, one obvious gap is that whatever proof we're doing is on design, not on the implementation, right? As I said, there's no hope I can do this on the implementation at all. The other gap what's interesting is that this taint method is fairly easy to understand, to implement, but in reality, it's actually causing additional flows, and there are features of the browser that it's extremely hard for us to handle to plug the leaks. So for example, in the browser, DOMs are synchronous, right? If I read the element, I get a pointer or get a value back right away. Now the question is, if I'm trying to read a DOM element that's been tainted, that contains secret, what should I do, right? So if I return a default value, the attacker would actually know that that this node has been tainted. Therefore, there's one bit of information leakage. If I return default value, you'll know. If I return error code, the attacker sees the difference. I cannot return the real value because that's a secret, right? So it's very hard to deal with. So instead, what we do is we just have the script get stuck, meaning it never returns. That allows us to prove our weak non-interference, but in reality this is still a leak in the sense that that's actually related to the scheduler, because the attacker knows that the JavaScript in general have a single-threaded loop. So if my script start running, suddenly I see the first 10 instructions being executed, but the 11th instruction didn't come. I know that my script gets stuck, right? Again, this is one bit leak of information. So this synchronous feature is really hard to handle. It would be nice if everything is asynchronous. Then I can use scheduler to actually hide some of the some of the information leakage. Yeah.
So when you think when you say it's a leakage of information, can you give an example what kind of leakage is this? Like,
let's say that
is it like my password was wrong? Is that how you know that I didn't put the correct password, or what kind of leakage are they?
So let's say that you hold a secret 0 or 1, right? You cannot directly talk to me because your label is high, my label is low. So instead, you is a variable. Initially, you're low. So I keep reading you. Your value has been 10 from the beginning. Then what you do to tell me 0 or 1 is to write to him or not. So if you write to him, now he becomes high because you tainted him. I've been reading 10 all the time. Suddenly, I don't either get an error code or get default value, or I didn't get any value back. I know something's up, because I know you told me if your value is 1, you're going to taint him. I know, oh, your value is 1. However, if I keep reading it, we probably should have agreement in terms of timing. If I keep reading it, I figure if you could have tainted him, you would have done it already. Now I know your secret is 0. So I can do this guess because of this synchronous operation plus the tainting the ref monitor is doing. So it's an implicit flow that we're allowing in our system, unless we actually have the script get stuck, meaning when I ask, I got terminated. I got nothing left. That's only a
but that also gives information.
That's also give information.
Yeah,
that's what
exactly.
I'm saying, right? That's also give information.
Unless you are always going to get terminated randomly, then
yes.
probably.
Then if I have a randomized scheduler, then I'm hiding this behavior, because I'm just saying, oh, the scheduler went away, did something else, instead of me getting stuck because I'm reading the tainted value. So it's very hard. I don't know. So the tainting, it's very weak. That's all that we're saying. It's an easy way to implement this kind of implicit leaks. It's really hard to actually plug these holes. Yeah. We'll probably have to go secure multi-execution that route. Anyhow, so the other part about scheduler. So we already talked about scheduler, right? If I just get you stuck, if I know the scheduler is deterministic, I know I'm getting stuck. Otherwise, if I have a non-deterministic scheduler, I could be thinking that scheduler might have gone away to do something else. So in our model, we actually in the model assumes a non-deterministic scheduler. That's why we can prove the non-interference. But in reality, JavaScript engine, different browsers implement things differently, but in general, they have one main thread for all the UI events. For the worker events, there's a concurrent thing, then there's a preemptive events, and so on. So there's a fair bit of complexity in the scheduler, but the attacker actually have some view about what scheduler can do at the back of their mind, right? So these are the gaps between what we do and the real sound proof at the end of the day, even at the design level. Yeah, so this is actually the gap where I'm trying to think about what's the best way to actually fix this. I mean, if one answer could be that I'm okay with 1 bit leak, then I'm done because I can only afford tainting. Or you can say I can go more expensive, then I might go up to secure multi-execution or do static analysis and so on. All right, so, yeah.
This is somehow random question. Like, so we know there is a lot of the timing channels in the browsers to tell the sort of the fingerprint in the browser, and what you're saying is something more aggressive. So this is starting with that, out of the fingerprinting the browser, you can somehow run the values if you have this sort of the feature like a stocking in the middle.
Yeah.
And so I kind of feel that the first thing the comes to my mind is that based on your label, maybe perhaps you can identify those timing channels because you sort of know the timing channels in this
Yeah,
case.
so that's one thing we want to do, right? So what we're saying is that for me to actually leak a lot of data, the attacker needs to exhibit certain behavior to leak it. If I can prove this, then my reference monitor can identify these behavior patterns to get rid of them. I don't have a formal theorem about it. That's what we're looking at as well. So how can we use this reference monitor to corner the attacker into a narrow corner so that they exhibit really deterministic patterns, certain API they have to use, then I can have another monitor to actually identify these APIs to stop them earlier. So yeah, so that's something that we're kind of interested in as well. It's hard to do a theorem about it right now, so it's in the experimental stage right now. Yeah. All right, so in terms of the gap between the real system, well, I have a gap. Yeah, I have a gap, right. So we have lots of complaints about policy. It's complex, right? It's hard to tell people what's going on. People are going to ignore it. We rely on the user to do stuff. And also declassification is very dangerous as well, right? So these are all the practical issues that I don't have the expertise to solve. We have to have experts in HCI. Hopefully, they will help us to solve some of these problems. All right, I think I'm running out of time. For the IoT stuff, it's really what's interesting about this is that when you use if this and that, essentially you can define rules to connect endpoints. So I can write a rule saying that if the weather is about 70, turn my nest to X temperature, right? I can also say if I receive email, store the extension to my OneDrive. So in this framework, you can write a lot of these rules. You can create a lot of information paths through different devices, right? Now things actually are not that rosy because I can have a rule saying when I'm on my road, I can say, oh, whenever I take an iPhone when I'm traveling, upload the picture to Flickr so everyone knows my fancy touring experience, like for example here. But since I forgot to turn this rule off, when I go home, I actually need to take a picture of my passport, and now this picture now shows up on Flickr, right? So you do have secrecy problems thinking about where the information, who can see my information. And then the dual side internal information flow on this problem with this is one of the integrity. So for example, I can write a rule, this is a real rule. If I can say if I'm tagging the photo, do a new status, right? This is useful if you're going to a party, your friends taking pictures, your friends tag you, then you have this nice states about you, Limin is at XYZ's party and taking a picture with what. But there are also unintended effects. If you're in some interesting gathering, you may not want people to know. So here you don't control the status update, instead it's other people controlling it, right? So that's the integrity issue. So here what we're doing is it's fairly practical work. We actually sift through all the public if this and that recipes, try to systematically analyze what's the problem, what's the secrecy and the integrity problem, right? So essentially, we view this as an information flow problem, figure out what are the secrecy labels we can assign to all these recipes, and same with integrity, and find problems there. So in terms of analysis result, I'm going to jump over this. So we look at all the recipes, about 20,000 unique recipes. Actually, half of them have some problem. So let's say I guess over the half, 33 of them actually have integrity problem, and another 27 of them actually have secrecy problem, and 10% have both of the problem, right? So this is like, if the designer have thought about information flow, they could have done some warning to the user, but people only thought about functionality, didn't really think about the security
where you get these
side.
examples from? Where you get these examples from?
There's a public recipe that one of CMU student scrubbed from IFT, where actually there's a database, we can actually share this, it's public shareable anyway. So they actually have an Excel sheet of all the recipes people actually use.
Oh, okay.
So we actually gone through all of them, yeah. All right, so I'm going to finish my talk with the last slide. So basically, I'm going back to this. There's difference between theory and practice. So if you do research on both ends, you talk to both people, both sides of the camp, you realize there's actually a gigantic gap between it. So if I'm in system research, my mindset often is, here's a really interesting idea. I'm going to implement this. I'm going to measure the performance and publish my paper. If I'm in the theory camp, what I do is, here's a really interesting intellectual problem. I'm going to build a model, define property, and prove it. Right. However, in reality, if you have software, I actually want to have both. Right. Well, I want to have nice features. I also want to have a pretty strong security guarantee. Right. So this gap is fairly wide. There are actually many interesting challenges when you actually look into the combination of these fields. I've done some work, but actually I'm nowhere near solving any of the, I would say, real problem. I'm still trying to make progress to actually solve additional problems here. All right. Any questions?
Yeah, yes, thanks.
Thank you.
Are there any questions? Maybe I'll start. So, in your first talk, when you mentioned about you generally talked about confinement or privacy or secrecy, but then there can be issues with the integrity, which it may happen that because somebody is able to play with the integrity, that they can actually infer some information. You didn't go into detail, but I assume that you have some already work or thoughts in that direction.
So, what I don't have is I don't have a nice theorem about the attacker cannot manipulate secrecy based on integrity. I had some of that in the previous earlier Android work, but yes. So in this example, secrecy is easy to explain. So we never touch upon integrity because the label is always empty. But in practice, what we do is we track integrity. So you can imagine there's interesting interaction between the secrecy and integrity. If maybe a low integrity attacker can cause secrecy to change, therefore leak information. I think our theorem actually covered that case, just because the equivalence, the projection come out to throughout all the different behavior based on the high label, and then I have to force all the low behavior to be the same. That will be ruled out.
Okay.
But I don't have a separate theorem about that.
Interesting.
Other questions?
Anything else? All right, then I guess you can ask question while talking to her now.
Thank you.
Thanks a lot.